So we discussed this procedure where we said we can arrive at the closed loop pole or the 3 dB bandwidth of a op-amp based circuit with a frequency independent frequency independent feedback network where your feedback factor beta doesn't depend upon frequency. So usually it's comprised of either resistors alone or capacitors only feedback networks. In such systems, we said that we can directly read the point at which the gain becomes unity and call it as the 3 dB bandwidth or the pole of the system. Now here, I just wanted to ask you guys a small question. What would happen? What actually happens to the phase of the system? See, what exactly is happening at that point? Why am I directly calling it as the pole? Remember, what is the definition of a pole? The definition of a pole is for any, since you guys have analyzed RC circuits and amplifiers and so on, we said that the definition of a pole, it's the point where your gain becomes equal to 1 by root 2 of its nominal value or DC value. For most circuits, let's assume they are low pass in nature, and for all those circuits, it's the point where your gain becomes 1 by root 2 of its DC value. Okay, how does that happen? So what exactly happens at a pole is that, let's assume 1 by S by omega 3 dB happens to be the frequency response of a system. At the pole frequency, you end up getting a response that looks like this. So which means the complex term, the magnitude of the complex term will be exactly equal to the magnitude of the real term, right? That's how you get root 2. Phase is 45 degrees, of course, but the more important thing here is the magnitude of this complex term will become exactly equal to the magnitude of the real term. The only thing I need to figure out when I'm plotting loop gain, I said this is the point where loop gain becomes equal to 1. So if I start with a closed loop system that looks like this, with a forward path gain of A of S and a feedback path gain of beta, the closed loop response can be written as A of S upon 1 plus A of S into beta. I can multiply and divide by beta and call this as 1 by beta into L of S by 1 plus L of S. Okay, so we said that this is the point when I find its magnitude of the loop gain becomes equal to 1 at omega equals beta times omega u. But what about the phase? I never spoke about the phase in the previous lecture. What do you think will happen to the phase? Use this approximation. Generally, the UGB of the op-amp will be much greater than the pole frequency, right? It will be usually gain times the pole frequency. And I can also make this assumption that UGB times beta will also be much greater than omega p. This condition also has to be met. Remember, what did we say? We said that if you want, I can have a very small beta. So when I multiply it with A, it should still be much greater than 1. Only then you get the benefits of negative feedback. A beta has to be much greater than 1. So if you guys recall, what is omega u? Omega u is simply A times omega p times beta. So this is simply A beta times omega u, omega p. Therefore, this will be obviously greater than omega p. So this assumption is valid. I can assume that omega u into beta will be much greater than omega p. Now, if I'm looking at the phase response of this system, it will look something like this. So so the phase response, it will start off at 0 degrees. It's a single pole system, right? So A of S into beta into A of S is simply beta into A upon 1 plus S by omega p. So it will start off at 0. When it reaches omega p, what will be the phase? 45 degrees. And after that, it will keep decreasing at the rate of 45 degrees per decade. Okay. So usually, if you guys recall, for the phase response, you should normally look at 1 decade before the pole, 1 decade after the pole. So if it's decreasing at the rate of 45 degrees per decade. So omega p by 10, approximately 0.1 omega p, you can start off, the the phase starts decreasing. At omega p, the phase will reach 45 degrees, and at 10 times omega p, it will reach 90 degrees and it will remain flat after that. A maximum phase shift that a single pole can cause is minus 90 degrees. Which means the phase response when we reach omega u will already, beta times omega u, it will already be minus 90 degrees. So remember loop gain, right? When I'm plotting loop gain, I'm plotting a complex number. So that's why a complex number will have both magnitude and phase. It is given that you know the magnitude of the complex number is 1 at what? At omega equals beta times omega u. And the phase of this complex number is equal to 90 degrees, which I can write it as j. Okay, so that's what happens here. So it's like I'm adding a complex number. The loop gain, the phase response is this. I'm adding a complex number, and the magnitude of this will be 1 by 1 plus j times, actually it is 1, 1 minus j times. So here you guys have to be a little bit careful. When I'll talk about what happens to the phase response. So let me just directly write it off. So it will be 1 minus j. Okay, and therefore L of s is simply, L of omega is simply minus j, because the phase is minus 90 degrees. Okay, and the magnitude is equal to 1. So that I can write it as simply equal to minus j. So the overall, if you will go back to the closed loop gain, I said some time back, the closed loop gain can be written as 1 by beta into L of s by 1 plus L of s. And if I take magnitude of this, right, 1 by beta, magnitude of j is just 1 divided by root 2. So you get 1 by root 2 beta. So therefore the gain becomes 1 by root 2 of its initial value, and this happens at the 3 dB bandwidth, or the pole of the closed loop response. So that's one intuition, because I just wanted to stress this point to show you guys how does the phase response of the loop gain look like near the unity gain frequency, especially for systems with fixed beta. So therefore I can treat them like a single pole system. So that's a very small detail. I just wanted you guys to know that. Okay, so later when we analyze more complex systems, we'll talk about terms like phase and gain margins. So right now this is sufficient to understand the frequency response of most of the op-amp based circuits with frequency independent feedback network.